And this week, we are going to jump ahead and start covering classification, and we will look at the Bayes classifier as kind of an example or an algorithm or a method that can be used for classification problems. In comparison to the 102B class that I teach during the regular school year, I did have to kind of trim a little bit of content just to kind of make sure everything fits within our summer schedule. If we happen to have time at the very end of the quarter, we can revisit some of those topics and stuff. But one topic that I had to cut a little bit was maximum likelihood estimation related topics for modeling and whatnot. And I know you've already covered maximum likelihood estimation in, say, 100B and some of your other courses. So I feel like it's not too huge of a loss, but again, just letting you know, there's a slight variation or difference between our courses here. All right, so anyway, as we take a look at this topic, the idea here is we have data and we want to classify the value that we are trying to predict is a category. Okay, we're trying to predict a category, and so you are kind of working on this already a little bit in your homework. With the neural network, you're trying to classify whether the data is Setosa or Virginica or versicolor, the iris species, and that's what you're looking at. And we just kind of said, oh, here's this neural network, and the neural network being such a kind of a flexible model, we just say, okay, well, the outputs is a single number, so that's regression. Or here, make multiple nodes in the output layer, and now you have a classification system. That's one of the, I guess, nice things about a neural network is just how flexible it is. But here I want to kind of take a look at a couple different algorithms or ideas here that are purpose-built for classification, right? And so the structure of our data is we have training data, okay? We have training data X, right? We have N observations, okay? And so that's what it means when we say we have N training objects. And so each observation in our data perhaps has several pieces of information. Each has dimension D. So again, if we're thinking about the iris data set, you have 4 variables. You have petal length and petal width and sepal length and sepal width, okay? And within your training data, each observation or each object has a class label. So these observations are class Setosa. These observations are class Virginica. These observations are class versicolor, and things like that. And so we have a total of C classes. So as far as iris data set goes, we have 3 classes, but we're not limited to that. And then the goal is, if we get a new observation, okay, a new observation where the class perhaps isn't provided to us, we want to be able to predict it. So we say, okay, here's a new flower, and we measured its petals, and it's 4.6, and its petal width is this and that, and its sepal length is this, and its sepal width is that. Can you predict which species or which class of iris is it? Okay, or perhaps you have a different data set, and we say, okay, well, if these are the numbers that we see, can we predict which class it belongs to, which category it belongs to? And so one thing to note is that we are using integers, we're using numbers to kind of label our classes, but we have to treat them as categories. Okay, so we might call Setosa class 1 and Versicolor class 2, or Virginica class 2 and Versicolor class 3 or something, but class 2 is not twice as big as class 1, right? It's not bigger or less or anything like that. And it's not meaningful to try to predict a value that's in between classes. Say, you wouldn't say this is a class 2.5 or something like that, or 2.3. That's not meaningful. You have to predict one of the classes, one of the categories. Okay. So, so what we're going to do is we are going to first look at the Bayes classifier. The Bayes classifier works by using Bayes' rule. Okay, Bayes' rule. It's a probabilistic classifier, and what that means is it is going to return a probability, all right? And that probability vector will add up to 1. So for example, if we have 3 classes, here I call them class A, B, and C. If we can say class A, this observation belongs to class A with probability 19%, class B with 80%, and class C with 1%, those 3 numbers add up to 1. That is different from, say, your neural network. The neural network that you're working on right now, those you get numbers between 0 and 1, and you're going to use whichever one's the biggest one as your class label. But those numbers don't have to add up to 1. They're not even probabilities. They're just numbers between 0 and 1 that kind of measure what the neural network believes the class is. But that's not. But it's not a probability. It's just a number. Okay, so those things don't necessarily add up to 1. Okay, another example of a probabilistic classifier is logistic regression. Logistic regression is used if you only have 2 classes, basically a yes versus a no, and you get, after you put it into the logistic equation, you get a number between 0 and 1, which represents the probability of basically yes. There's other kind of families of classifiers, and so you have, say, the k-nearest neighbors or the support vector machine, and these use maybe what we call hard rules, and they will designate a class without using a probability. Okay, and it just says the model predicts class B, or just gives a number here. Okay, and the Bayes classifier is an application of Bayes' rule, but it's important to distinguish this and say that the Bayes classifier is not Bayesian statistics. Okay, the Bayes classifier is not Bayesian statistics, which is kind of a whole different mindset that involves treating parameters as random variables. Okay, that's coming in a different course. So anyway, just to review, this is Bayes' theorem. Bayes' theorem says the given probability, you have this probability of A given B can be found by doing the probability of B given A times the probability of A. This is equal to the probability of A and B, or the union of B and A. All right, I'm sorry, not the union, the intersection of B and A, probability of B and A up here can be found this way. And we divide by the probability of B. Okay. We can expand this denominator, probability of B, using kind of the law of total probability, and we can say, we can calculate basically the numerator, the probability of B given A for a particular value of A, multiplied by the probability of A. We can do this across all possible values of A, and this would be the total probability B. Okay, so yeah, so we can kind of calculate the total probability of B by saying, okay, what's the probability of B given A times the probability of A plus what's the probability of B given, a different class times, times the probability of that thing. So, for example, we can ask, what is so we can say there's, people have the disease. Okay, so we can say someone has a disease, and it's either yes or no. Okay, so we can say probability disease versus probability of no disease. And then we can say if someone has the disease, they have probability of positive given disease. This is testing positive, right? And we'll say 99% chance testing positive. Okay, and then we'll also say, even if someone does not have the disease, we'll say they have a, 2 chance. This is the false positive. And that would be the probability of positive given no disease. Okay, so the total probability of testing positive would be is equal to probability of positive and having the disease plus the probability of testing positive and having no disease. And this part is equal to the probability of positive given disease times probability of disease. And this part is probability of positive given no disease times probability of no disease. Okay. So this is basically what we are doing here. We're saying the probability of this numerator, or I'm sorry, this denominator, the probability of just kind of everybody testing positive can be decomposed into the product of B given, whatever class times that the probability of that thing, summed across all possible values of this. In this case, we have disease versus no disease. That's the kind of the different classes. And if you had like multiple classes, you can kind of get this value across all of the different possible values. Okay, so here is our goal. We want to know the probability that some new class label. All right, what is the probability that this new observation belongs to category C? Okay, we want to know the probability that the class label of some new observation is equal to some particular class label, and it's going to be based on basically all of the values in this new observation, and kind of given our training data, which is the input values X and the training labels T. All right, couple rules. It's a probability, so the result, the answer has to be between 0 and 1. And then because it is a probability, if we add up the answer across all of the different possible categories that we have, those answers have to add up to 1, right? So again, if we had 3 categories, A, B, and C, the probability of being A, probability being B, and probability being C, those things have to add up to 1. All All right, and so this is how we're going to apply Bayes' rule. This is the thing that we're going after. We're trying to get what is the probability that our class or our observation belongs to class C given the X values. So this is kind of our A given B. And using Bayes' rule, we're going to switch around to probability of X nu given T nu equals C times the probability of T nu equals C divided by the probability of X nu in the denominator, right? So this part, this is known as, this part here, this is our posterior distribution. This is the probability we want to find, the probability that some observation belongs to a particular class. That's what we want. We're going to find this by calculating the likelihood. The likelihood is, what is the probability of getting the values within this X vector, right? So what are the probabilities of getting the values that we have in the X vector if it came from class C? Or what's the probability of getting this X vector values in the X vector if it came from, some other class, okay? Maybe certain classes are more likely to produce certain values than others, okay? And then we multiply that by the prior probability of saying, okay, what is the probability that just some new observation belongs to a certain category or class before we even looked at any of the measurements in X, okay? So before we looked at any of the measurements in the particular X vector, what was the probability that it belonged to that class? And then in the denominator, we have what's the probability of getting the values within that vector X nu, regardless of the class label. So if we just kind of consider all of the different possible classes, what's the probability of getting those values, okay? All of these things have X and T in the given part because all of these values are based on the training data that we have, the X and the T training data that we have. All right, so this is kind of this big formula. And I think it's going to make most sense if we work through an example, okay? Oh, and then again, this denominator part, we can expand it. We can expand this denominator by saying we're going to sum the numerator across all possible classes. So again, using kind of the law of total probability, we're going to say, well, this thing can be expanded to whatever the numerator is, but we're going to consider all of the different possible categories. Okay. All right. So again, let's just try out an example. I think, well, I hope, my hope is this example will help clarify what it is that we're talking about. Okay, but before I get into that, let me go ahead and give you your first view quiz answer. Your first view quiz answer is the letter B. B as in bear. B as in bear is your first view quiz answer. Okay, so this is a silly example, but I hope it works. All right. So we are going to one day decide we are going to buy a whole bunch of marbles. Okay, and you go on the internet and you say, I'm going to order 25 bags of marbles. Okay, and the marbles, they come. It's a mix of red and blue marbles. Okay, so you get these bags, inside them, these little marbles, some are red, some are blue. And anyway, all of these things arrive from the factory, and we see that the marbles are filled at 3 different factories. There's factory A and factory B and factory C. And it seems like, oh, you know what, factory A fills the marbles up at a different proportion than factory B, and might be different from factory C, and so on and so forth. We go through and we have, we bought 25 pouches, 24 of them are labeled, but the 25th one, the last one, is not labeled. And what we want to do is we want to try to guess which factory it came from. According to the labeled data, factory A, there were 12 that came from factory A, 6 that came from factory B, and 6 that came from factory C. For factory A, we have 12. Factory B, we have 6, and factory C, we have 6. Okay, so this is kind of what we have in our training data. So, 25 bags of marbles, 24 of them are labeled. This is kind of our test case, and we want to try to figure out, which factory did it come from. Okay, so we go and we investigate all of the different bags that we have. Okay, and what we find is in the training data, okay, factory A is 60% red. Okay, so that is to say, probability of red given factory A. All right, so I'm going to just say red given A is equal to 60%. Right, and then we look at all of the data in factory for all of the bags coming from factory B, and we get 50% of the marbles in factory B are red. And then in factory C, it seems that only 40% of the marbles in factory C are red. Okay, so I'm going to write it like this. So the probability of getting red, if we know it comes from factory A, is 60%. The probability of getting red if it comes from factory B is 50%. The probability of being red if it comes from factory C is only 40%. Okay, now here the truth is we don't actually work at the factories, and we don't know the exact filling proportions. And so, when we open up these pouches that come from the factory, they got some variation. All right, maybe some of the pouches from factory C are 42% red, and some are 35% red, and maybe some are even 50% red, but we know it comes from factory C. Okay, and okay, so I got some of these examples, but we're going to go ahead and kind of assume that there's a binomial process filling up these bags. Okay, and so these are just kind of the summary stats, and we do this by kind of doing basically maximum likelihood estimation, which basically says that, okay, in your data, if 60% of your data is red, then the maximum likelihood estimate for what the proportion at the factory in the population is will also be 60%. Okay, so what we want to do is we want to look at our test case. Okay, and so we look at our test case, the one bag that we have, and we have 20 marbles, 10 are red. That's what we've got. Okay, 20 marbles, 10 are red, and the question is, which factory did it come from? This is the Bayes classifier here. So this is what we have. So in our training data, factory B is 50% red. So we go, oh, well, you know what? My test case is 50% red. So maybe it comes from factory B. But then we look at if we look at the classes, it looks like factory A produces more bags than the other factories. So maybe it's factory A. Okay, so we want to kind of combine these two kind of competing ideas. One says, okay, factory A is producing half of our things. And then the other thing says, well, our data looks most like factory B. So maybe it's coming from factory B. And this is what we want to try to figure out. So first, we're going to find the likelihood. The likelihood is asking the question, what's the probability of getting our data if we assumed it came from this factory, or if it belongs to this class? Okay, and so we're going to say, okay, what is the probability that I would get 10 red marbles if I assumed it came from factory A? What is the likelihood I would get 10 red marbles if it came from factory B? What's the likelihood I would get 10 red marbles out of 20 if it came from factory C? So in this case, we're assuming kind of this binomial process, right? So binomial, I'm assuming you guys remember your binomial distribution, which is we're repeating a trial n times. We're picking 20 marbles at random. And every time we pick a marble, it could be red or blue. And so basically when the factory is filling this up at a high rate, but it's just doing this very, very quickly, you know, the 20 marbles it fills the bag is basically 20 random marbles being selected. And, you know, the probability that a marble is red or blue is going to be equal for every marble that's being selected. And we want to know what's the probability we get 10 red. What's the probability we get 10 red? So we're going to do n choose x, so 20 choose 10, p raised to the x, in our case 10, times 1 minus p raised to the n minus x, which will also be 10. And so for factory A, this probability, this p that we're using is going to be 0.6, okay? Right? So if for factory A, the probability of it being red is 0.6, the probability of being not red is going to be 0.4. For factory B, the probability of being red, p is going to be 0.5. And then for factory C, the probability that p is red is going to be 0.4, okay? And so we go through our calculations. We have 20 choose 10, 0.6 to the 10, 0.4 to the 10, and we get something around a little under 12%, 0.117. For factory B, we get a likelihood a little under 18%, 0.176. And then here for factory C, we also get the same likelihood as factory A, 0.117 here, okay? So according to the likelihood, which is basically looking at these proportions alone, factory B has the highest likelihood, which kind of aligns with what we know. From our training data, we know 50% of the marbles coming from factory B are red, and when we opened up our bag was 50% red. So going off of just what we see in the data, this factory B seems to have the highest likelihood. But now we need to take into account kind of this prior probabilities, which says, you know what, if we didn't open the bag, right? If I didn't open the bag and if I didn't look inside what was in there, and I just said, hey, which factory do you think it came from? Well, we would say, well, you know, factory A is producing like half of our bags. And so, you know, we would have, prior to opening the bag, we might have guessed factory A, okay? So prior to opening this bag, what's the probability it came from a particular factory? You know, this prior probability is just the probability that some new observation belongs to a class C before we learned anything else about it. And so here, according to our data, according to our sample of 24, half of the bags, 12 out of 24, came from factory A. So our prior probability for factory A would have been 0.5. And then similarly, we would have said, okay, well, 1/4 of the bags came from factory B and 1/4 of the bags came from factory C. So the prior probabilities for factory B and factory C would also each be 1/4 or 0.25 here. Okay, so those are our prior probabilities. All right, is that okay? Likelihood, how we're getting these numbers, and the priors, how we're getting these numbers. I just kind of want to make sure these ideas are good with everybody before I keep going here, because otherwise the rest isn't gonna make sense. Okay, well, no one's saying anything, but I hope it makes sense. Okay, all right, thank you for your thumbs up. All right, so what we're gonna do is we're going to multiply the likelihood and the prior. All right, we're going to just multiply the likelihood and the prior for all of the different classes. Okay, so I say, okay, so the likelihood numbers, 0.117, 0.176, and 0.117 we have, and then the priors, 0.5, 0.25, and 0.25. Okay, so we just take the likelihood and we multiply it by the prior. And we do it, okay, what's the likelihood times the prior for class A? What's the likelihood times the prior for class B? What's the likelihood times the prior for class C? Okay, so if we understand where the likelihood numbers are coming from, which in our case we use the binomial, and if we understand where the prior probabilities are coming from, and we just kind of use the proportions, we multiply those two together, and we get basically these numbers. These are the numerators. All right, and then and basically all our work is pretty much done at this point. We just have to kind of scale these up so that if I were to add the numbers together, they add up to 1, the probabilities together. So what I'm going to do is I'm going to add these things up, and that's going to form the denominator, right? So if I told you, okay, you have these three numbers, 0.058, 0.044, and 0.029, and I want you to scale them so the sum of them add up to 1, what you would do is you would add these things up, and you'd say, okay, well, these three numbers, they add up to, I don't know, like 14%, and we're going to now divide each number by 14%, and now the three numbers will add up to 1. And that's exactly what we do. We just take these numerator values, right, and I add them up, okay? So I'm taking, this is the numerator. We have three different values. I got 0.058, 0.044, 0.029, okay? It's just these numbers, 0.058, 0.044, 0.029. I take those three numbers, I add them up, and I get 0.131, okay, or 0.132, so about 13%. And now I take these numbers, each of these numbers, and I divide by this, and I'll get a new number, and those new numbers will add up to 1. So this is the denominator. The denominator is just the sum of the numerators found for all possible classes. Okay, so this final answer, what is the probability that something belongs to class A? I just take that numerator, 0.058, and I divide by the denominator, 0.132, 0.1319, okay? And I'm going to get 0.444, okay? If I wanted to kind of expand this out to match the formula, we're asking, what is the probability that our observation belongs to class A, given the data that we saw? The data that we saw was that we got 10 red marbles out of 20 marbles, okay? And along with all of our training data. So, so to answer this, we said, well, what's the probability of getting 10 red marbles if it came from class A, which has a probability of 0.6, okay? And that's the binomial. 20 choose 10, 0.6 to the 10 times 0.4 to the 10, okay? Multiplied by the prior probability, which is just what's the probability that some observation belongs to class C, what's the probability that it belonged to class factory A? And according to our training data, that was just 12 out of 24.5, right? And then we divide by this marginal probability, which is the probability of getting 10 red marbles regardless of factory. And so I would have to calculate this numerator across factory A, factory B, factory C, the three possible classes, and I get this number. All right, so I get 0.44 for probability of being class A. I do the same thing for class B, and I get around 0.33. And it asks what's the probability for class C, and I get 0.22. Right? Same kind of calculation. I just take that number, these three different numbers, and I divide by the sum of the three values. And now 0.44, 0.33, and 0.22 basically add up to 1. Okay, with a little bit of some rounding, we'll get something right around 1. Okay, and that's the calculations that go into the Bayes classifier. Now here's a couple things just to kind of point out, is that our test case was 50% red. Okay, and so again, if we were to base our classification based on that only, we would have probably guessed class B, because class B is most like is 50%, and our data resembles class B the most. But we're also, the Bayes classifier also takes into account kind of the prior probabilities, which was specifically in this case, it said, well, half the bags come from factory A and only a quarter of the bags come from factory B. So after we take that into account, both of those things, the kind of the competing things, then the result was that factory A has the highest probability of around 0.44. So if I didn't look at the data, I would have guessed factory A has probability 0.5, right? Because half of the bags come from factory A. After looking at the data, factory A is not as strong of a contender because the data don't quite align with factory A. Factory A is 60% red, and our bag is only 50% red. So factory A loses a few points, and it comes down to 44%. Okay. Meanwhile, factory B, prior to looking at the data, we would have given it only basically a 25% chance that it came from factory B. Okay. After looking at the data, because my data aligns with what we know about factory B, and that half of the marbles from factory B are red and half of my marbles in the bag were red, that bumps up factory B's probability from 25% to around 33%. Okay. Meanwhile, factory C, prior to looking at the data, we would have guessed factory C was 25% chance because only a quarter of our bags came from factory C. And after looking at the data, it actually loses some points because, well, our data don't quite align with factory C. Factory C we know is 40% red. Our data was 50% red. So factory C loses a few points and it becomes less probable. From 25%, it drops down to 22%. Okay, we have a question. Yes, Taylor.
So for our test case, that's just our 25th bag that we're trying to find, right?
Yeah, the test case was just an arbitrary bag. In our case, I said it is the 25th bag. There's 20 marbles in it. 10 of them are red and 10 are blue.
Oh, okay, that makes sense. Thank you.
Yeah. Okay. Now there's a few like major assumptions that we made, and if it turns out that our assumptions are wrong, then maybe our whole thing is no good. One is the story I told was that we opened up the bags that we have. We opened up the 24 bags, and I said, okay, well, these bags are labeled factory A, and after opening up all of these bags, 60% of the marbles are red and 40% are blue. Therefore, I'm assuming factory A is 60% red. Okay, that's a big assumption, right? We're assuming that the bags that we bought from the internet is representative of how this factory is operating, and it may or may not be. Okay, that's kind of what we're assuming. And then the other big assumption was that, okay, when I bought 24 bags and half of them came from factory A, I'm now assuming factory A produces, has twice the output of factory B and C, because in my sample, factory A, 12 of them came from factory A and 6 came from factory B. So that's also a big kind of assumption there. But it's possible, regarding this second assumption where we said, when I bought these 24 bags and half of them came from factory A, somebody else might be familiar and they say, oh, you know what? I work for Marble Factory or the Marble Company. And I know factory A, B, and C, actually, they have the same amount of marble output, right? Factory A, factory B, and factory C all produce marbles at the same rate. And so when you buy a bag of marbles, you have an equal chance of it coming from factory A, B, and C. And if you have that knowledge, you can incorporate that. And you would just say, okay, before I even open a bag, I'm going to assume there's a 1/3 chance that it comes from factory A or 1/3 chance that it comes from factory B. And so, so we can use that, all right? So your specific kind of domain knowledge will affect how you model these prior probabilities. Okay. Taylor, did you still have a question?
Oh, no, sorry, I just forgot to lower. Thank you.
Okay, no problem. Okay, let's just try the same exact example, but this time we will change what we see in the bag. So this time we open up our bag, okay, and in our bag we have 20 marbles and only 6 of them are red. Okay, so 6 out of 20, so that's 30% red. Okay, and so now we ask, okay, well, which factory did it come from? Okay, so again, prior to opening the bags, we would have said factory A is 50%, factory B is 25%, factory C is 25%. Okay, but we open up the bag, and now it's only 30% red marbles. Okay, and we go, oh, geez, there's hardly any red marbles in there. Now, could it have come from factory A? well, what's the likelihood of getting only 30% or 6 red marbles out of 20 marbles if it came from factory A? Okay, well, we'd say, okay, well, 20 choose 6, 0.6 to the 6, 0.4 to the 14, multiplied by its prior probability of 0.5. Okay, and we get this value of 0.002, pretty small number. Okay, what about factory B? Factory B normally fills up 50% probability red, and we only get 6 out of 20. So we do 0.5 to the 6 times 0.5 to the 14. We're going to multiply that by its prior probability of 1/4, and we get 0.009. Okay, what about factory C? So factory C fills up with a rate of 40%, and so it's not too hard to believe that it could have just filled up only 6 red marbles, right? Because 6 with a fill rate of 40% red, we would have expected something around 8 red marbles, 8 out of 20 red marbles, and we only got 6. That doesn't seem too far off, and we multiply that out, and we get 0.03. Okay, so I get 0.002, 0.009, and 0.031. If I add these numerators across all possible values, I get a denominator of around 0.042, 0.04277. And so now I'm going to take each of these numbers and divide by the denominator. And so after doing this, factory A is the least likely with a probability of less than 6%. Factory B has a probability of around 22%, and factory C has a probability of around 73%. Okay, so again, after we take into account the data, and in this case, our data is quite different from factory A, right? We got 6 out of 20, so versus factory A, we would have expected 12 out of 20 marbles to be red, and in our case we only got 6 out of 20. So that makes factory A kind of very low on the list of contenders, and factory C, which fills bags at a rate of 40% red, is the most likely factory for this particular bag that we have, which is 30% red. Okay, and so that's the Bayes classifier, and I hope this example kind of illustrates how we're going to incorporate the likelihood along with our priors to calculate our values. Okay, and so in some of the examples that I do in the future, I basically just calculate the numerators, and then I don't really get into calculating the marginal probabilities in the denominator, but it's not too hard because you're just basically taking the numerators and you're just summing up the numerators across all of the different possible classes that we're considering. Okay, so here I just say factory A is the least probable, and factory C is the most probable after taking a look at that data. Okay, so let's expand this and take a look at a multivariate Gaussian. So rather than just this kind of silly example with marbles and the binomial distribution, let's look at something maybe a little bit more practical, and we'll look at a mixture of multivariate Gaussian distributions. Let me give you your second view quiz answer. Today's second view quiz answer is the letter E. E as in elephant. E as in elephant is the second view quiz answer. Okay, so this is the PDF of the multivariate Gaussian or the multivariate normal distribution. All right, here we are saying each value X, each observation X is a vector of length D. This is your data comes in D dimensions, and it's 1 over 2 pi raised to the D over 2 times the determinant of sigma to the 1/2 e to the negative 1/2, and here is x minus mu transpose the sigma inverse times x minus mu. Okay, Mu is the mean. It's a vector of means, all right? And the variance is a d by d matrix, the variance covariance matrix of the x variable. And if the off diagonal elements in sigma are 0, then the x variables are independent, the individual x variables within x. And you could then factor the multivariate PDF into a product of univariate normal PDFs as well. But anyway, let's just kind of here, let me look up multivariate normal distribution. I will also look up the normal distribution. So I do kind of want to point out that the PDF, here's the PDF for the normal distribution. And if you compare the PDF for the normal distribution with that of the multivariate normal distribution, there's actually quite a few similarities, right? So I've got basically like a root 2 pi, square root of 2 pi. And we have this 2 pi raised to the 1/2, but we're raising it to the d times 1/2. Okay. You take, here I have the standard deviation or the square root of the variance. And here I have basically the determinant of the variance raised to the 1/2. So kind of like the square root, but it's just now you're dealing with a variance matrix. I have e raised to the 1/2 times x minus mu over sigma squared. Okay, but now we're dealing in matrix form. So I still have this negative 1/2. But in matrix form, I've got, instead of x minus mu squared, I've got x minus mu transpose times x minus mu. And then instead of dividing by, this thing squared it, instead of dividing by the variance, sigma squared, there's no such thing as matrix division. I'm going to multiply by the inverse of the sigma matrix. Okay, so lots of similarities. It's just kind of expanding the normal distribution PDF into a kind of a multivariate form. So what I'm going to do is I'm going to use this R package, R library called Nvt Norm for the multivariate normal. And it's going to generate some data here. And I'm going to generate data from 3 classes. I've got class A, which has a mean of 2, 3. Class B has a mean of 0, 0. And class C has a mean of 2, negative 2. So if you imagine kind of your data, you've got class B right in the middle at 0, 0. Class A is a little bit to the up and to the right at 2, 3. Class C is to the right and down, 2, negative 2. The variance matrix for A is we have 3 and 1 in the diagonals and zeros in the off diagonals. So those x1 and x2 within class A are independent. Similarly, for class B, you got it's the identity matrix. You've got 1 and 1 in the diagonals and 0 and 0 in the off diagonals. Whereas for class C, we have 3 and 3 in the diagonal and 2.5 in the off diagonal. So there is some covariance here. And so if I generate the data and I plot it, so this is just code to generate the graph, this is kind of what it looks like. All right, so I've got these kind of representing contours of the multivariate normal distributions. So we can see red is centered at 2, 3, blue is centered at 0, 0, green is centered at 2, negative 2. Okay, and then there is no covariance between x1 and x2 for red, no covariance for x1 and x2 for blue, and there is covariance between x1 and x2 for green. And so we have this, our ellipse is kind of tilted over here, and whereas over here, because these have the same variance, 1 and 1, they're circles, and over here we have different amounts of variance for x1 has a variance of 3 and x2 has a variance of 1. So here the ellipse is wider over here. So this is what our simulated data look like. Now, when we are doing the multivariate normal classifier, we don't actually know we don't know these properties that generated the data, okay? We have to just look at the data and we have to kind of infer what the mean of the green class is. We have to figure out what the mean of the blue class is and figure out what the mean of the red class is. We don't actually know. Here we generated the data, so we do know, but what we're going to do is we're going to kind of pretend that we don't know these values, so it's a little bit more like real life, okay? So to kind of estimate the mean, we're just going to take the mean of the observations, okay, that belong to that particular class. So I'm going to just say, okay, what are the observations that belong to that particular class? And let's take the mean of those observations. All right, so here I'm going to just say, okay, for the observations that belong to class A, okay, for the red observations, what's the mean in X1 and what's the mean in X2? And it says, okay, your mean in X1 is 2.267 and the mean of X2 is 2.82, right? Now, the true values that generated the value, we had a mean of 2 and a mean of 3, and we're getting kind of close to that, but not exactly that because of randomness, right? For generating class B, we know that the true mean is 0, 0, but when we take the mean of our observations, we get a mean of 0.3 and negative 0.1. And then for class C, the true values were 2, negative 2. And when we just take our random sample of data and calculate the mean of our sample of data, we get 2.25 and negative 1.91. As far as estimating the variance, we'll take our observations and we'll calculate the variance here, okay? The maximum likelihood estimate for the variance is this. Basically, you do x minus mu squared, but in matrix form, x minus mu transpose, x minus mu, and you divide by how many observations you have. The kind of the unbiased estimate for the variance, though, is you divide by n minus 1, right? So the maximum likelihood estimate is 1 over n, but this is going to produce biased results for our population, what do you call it, variances. And so to kind of get the unbiased, we divide by n minus 1, right? And the reason why we do this, well, it's called Bessel's correction, but when you use this value, you are going to underestimate the amount of the mean in the population, because if you knew the true value of the mean in the population, you could just use that. You could take each observation, subtract off the true value of the mean in the population, and you would get an estimate for what the average distance from the mean in the population is, right? The variance is kind of like, what's the average distance from the mean, average square distance from the mean? And if you knew what the true mean of the population is, you would just take each observation and say, okay, it's this far from the true mean of the population. But what we're doing here is we don't actually know the mean of the population. We're taking the mean of our sample. And the mean of our sample is always going to be in the middle of our sample. And so when we say, okay, what's the distance from the mean of our sample? The distance from the mean of your sample is always going to underestimate the mean from the true value in the population. So, so when you take these distances from the mean of your sample, it's going to underestimate the distance from the mean of the population. And so to kind of compensate for that, instead of dividing by n, we divide by just a tiny number that's a tiny bit smaller, n minus 1. And that actually fixes the amount that we're underestimating by. So that's why we divide by n minus 1 rather than n. But anyway, all to say, we can just get the estimates of our variance by calling variance in R, right? So we take the observations that belong to class A, we ask what's the variance of that, and we get kind of these variance things, okay? And so if I plot that, this is kind of what the estimated centers and contour lines look like. So this is kind of the normal distribution fit to our red data. This is the normal distribution fit to our blue data, normal distribution fit to our green data, okay? And if we look at that, we go, oh yeah, this is centered right in kind of the center of our blue, centered right on our green, centered right on our red. And if we compare that to the original values, so if you look at the the ones that generated it, okay, our blue dots happen to be a little bit off center from the true values. And so, we get similar graphs, but not quite exactly the same because, this is subject to randomness. And so this is what we've estimated. Whereas, the true values we know were generated from here, but that's fine. This is what we're dealing with. And in real life, we don't actually know the mean of the populations. So we're estimating them based on the data that we have. Okay, our data are labeled. We know that these ones are red and these are blue and these are green. So we're trying to get our population estimates. Okay, so let's try out the Bayes classifier here. Okay, let's say I put a test case. We generate a new data point right here at 0, 0. And I say, okay, looking at the training data we have, red points are over here, blue points are over here, and green points are over here. What class do you think this dot belongs to, right? And we look at this and it's very easy. And we go, okay, that's got to be blue, right? If it's right there, it's got to be blue. But let's check the math and see if it lines up with what we have. So we use the Bayes classifier, and we're just going to say, okay, what is the likelihood multiplied by a prior probability divided by the marginal probability? We're going to say the probability that it belongs to class blue is going to be the likelihood that blue generated a point at 0, 0 times the prior probability divided by the marginal probability. But basically, let's just look at these numerators here. So the likelihood is just kind of a matter of plugging in our value into the normal PDF. Okay, right? So we've got the multivariate normal PDF, and we're going to say, okay, well, what's the normal PDF of getting 0, 0? Okay, so, or actually for class A, we'll say, okay, what's the probability of getting, what is the probability that this class, right? The class centered at 2, 3, but not exactly that. I think it's centered at 2.2, 2.8 or something based on our data estimates. The mean of class A, yeah, 2.26 and 2.8. Okay. If we had a normal distribution centered at 2.26 and 2.8, could it generate a point at 0, 0? Sure, it could. It's not very likely to, but it could, right? And so to do this, I can use the normal PDF, and I do 1 divided by 2 times pi raised to the d over 2, 2 over 2, times the determinant of the variance raised to the 1/2 power, times e to the negative 1/2, times the transpose of x, which is 0, 0, minus the mean x bar, times the inverse of the variance, times x minus x bar. Okay, and if I go through all of this formula, I get the number 0.000879. Okay, so I get a pretty small number. This is the likelihood, or the result of plugging in our test case 0, 0 into the normal PDF. Okay, so here we're using the multivariate normal distribution. Does the Bayes classifier work for any distribution? Yes. So if you know the likelihood, what distribution you want to apply, then yes, it will work. So, again, for the Bayes classifier, we just saw an example where the likelihood was calculated using the binomial, right? So we did it with the binomial. Now we're doing it with the multivariate normal. Okay, as long as the output is categorical. No, well, the likelihood, you do a likelihood calculation. It's a numeric value. Just you have to say, how do I calculate it for a particular class? So here we're doing it for class A, and we're plugging in basically the mean of class A and the variance of class A into our formula. Now this formula is kind of annoying. It's fine. It is what it is. Thankfully, in R, there's a function called give me the density of the multivariate normal. And that's exactly what we're going to do. So if I say, hey, give me the density of the multivariate normal, we're going to plug in x new is 0, 0. the mean, the mean is going to be X bar and the sigma is the variance, okay? And if I plug this in, this gives me the likelihood and tells me, oh, your answer is 0.00087953999, which is exactly what I got when I kind of plugged it into my formula, my PDF formula manually, okay? So here I get this number. I don't actually have to do that. I can just ask, give me the density from the multivariate normal, okay? And we do the same thing for class B and class C. We use the mean of class B and the variance of class B, the mean of class C and the variance of class C, and we get the likelihoods for class A, class B, and class C, okay? And so we can see from this, class B has the highest likelihood, 0.1654. Class A has a lower likelihood. And class C, it says, you know, if your distribution is looking like this, to end up coming all the way over here is very unlikely, 1.6 times 10 to the negative 5. So that's the likelihood. The prior probabilities would just be, you know, before we even looked at the data point, would you have guessed it was, you know, red, blue, or green, class A, B, or C? Well, our prior probabilities here, if we just, I think we had 90 points total, and each, there were 30 red points, 30 blue points, and 30 green points. So our prior probabilities would just be 1/3 for all three classes. Okay. The marginal will be found by taking the numerator and adding them up for all three classes. So I'm going to do the likelihood of class A times the prior of class A plus the likelihood of class B times the prior of class C plus the likelihood of C times the prior of class C. And we would add them up. Now, technically, I don't even have to do this because the three priors are exactly the same, but just for good practice, we'll multiply them by the priors and add them up. Okay, and then we do the likelihood times the prior divided by the marginal. Okay, so I take the likelihood times the prior divided by the marginal. And after doing that, class A has a posterior probability of 0.005. Class B has a posterior probability of 0.9946. And class C has a posterior probability of 9 times 10 to the negative 5. So class C is very unlikely. Class B is by far the most likely with over a 99% probability. And class A is quite unlikely with a probability of about 1/2 of 1 percentage point. And that aligns with what our visual inspection says. And we say, okay, if you see a dot here, what class do you think it belongs to? And we would all say, yeah, it's got to be class B. Okay, it's got to be the blue one. Okay, let's try out this one. Here I've got this dot over here. Do you think it's class red or do you think it's class green? Okay, this observation is at 6.2. What do you guys think? All right, this is probably not going to be class B. We would expect higher numbers for the red and the green. And if I had to guess, maybe a little bit more likely red because it's still inside this ellipse, and over here it's outside of the ellipse for green, but I don't know. That's my guess. So here we just kind of go through and we say, all right, our observation is at 6.2. Let's calculate the densities. So this will give us the likelihood for class A. I've done this all on one page now. Density for class A, or likelihood for class A, likelihood for class B, likelihood for class C, using kind of the mean of A, B, and C and the variance of A, B, and C. And then the prior probabilities are 1/3 for everything. The marginal, which is the denominator, is going to be likelihood times prior, plus likelihood times prior, plus likelihood times prior for all three classes. And then we do likelihood times prior divided by the marginal for all three classes, and we get class A is around 79%. Class B is 10 to the negative 9, so very almost zero probability. And class C has a probability of around 21%. Okay, so kind of what we expected based on this. If you get an observation out here, we're saying it's 80% class A and 20% class C. So 80% red, 20% probability of being green. And, you know, pretty much zero probability, not zero, but very low probability of being the blue dot. Okay. And that's what we have. Okay. And we can kind of mess around more. All right. What if we do this? All right. Is this one more likely to be red or green? So you go through the calculations. Again, here the observations at 5, 1. You plug that in. You get the likelihood for each of these classes. The priors 1/3 for all of them. You find the marginal probability, you do all of these things, and we get, now it's around 39% for class A and 61% for class C. Okay, here's one where, you know, I intentionally picked a kind of a weird spot here. This one I put 2.53, 0.37. It's kind of at the intersection of all three of these things. What do you think? Is it red, blue, or green? And the Bayes classifier kind of comes back and says, yeah, 30% class A, 36% class B, 33% class C. But, you know, these are all kind of well within striking range of each other. You know, it really is a toss-up. If your observation is right here, you know, it's really a toss-up as far as which class it belongs to. Okay. All right, does that kind of make sense as far as the Bayes classifier goes? And this time we're using the multivariate normal distribution. Questions here? Thumbs up. How many view quiz answers did I give you? 1, 2? Have I given you the second one?
I think.
I gave you 2 view quiz answers or 1 view quiz answer? I don't remember.
Just 2.
You gave us 2. Okay. All right. Well, great. I will keep going. I'll give you your 3rd view quiz answer later. Okay. So again, the posterior probability we find by doing likelihood times prior divided by the marginal. And the marginal is just found by taking this numerator, the likelihood times the prior, and we're adding them up across all possible classes. Okay. I want to expand this and introduce the naive Bayes classifier. So we have the Bayes classifier, and highly related is the naive Bayes classifier. Okay, so what's the difference between the Bayes classifier and the naive Bayes classifier? Okay, well, if we revisit this multivariate normal distribution, you know, this is kind of our PDF, and it's kind of a it's a little complicated. Now, thankfully, R makes it easy for us by having the multivariate normal package, and it calculates our stuff for us. But the naive Bayes classifier just says, you know what? Let's assume the x variables are independent of each other. Let's assume the x variables are independent of each other. And so we would just break down the multivariate and just turn it into a product of univariate PDFs. Okay, so we would say, all right, the multivariate PDF, we're going to just say is the product of, you know, the normal distribution for x in x1 and the normal distribution for x2. So, so if you take a look at kind of, so the multivariate normal PDF, overall, it looks like an ellipse, okay? But if you kind of take the marginal probability, right? If you integrate out one of the variables, all right, in this case, it's xy. If you integrate y and you look only at the distribution of x, it follows a normal distribution. If you integrate out x and you look only at the distribution of y, it too follows a normal distribution. And what we're going to do is we're going to just say, all right, you know what? We're going to approximate this distribution by just taking the product of x and y. Let's just take the product of x and y. I'm going to treat them as independent. we're treating them as independent variables, or x1. Sorry, I don't know what's going on here. 1 second. Alexa, stop. So we're going to kind of just treat these things independently and just take the product of them. So here, that's what we have. Okay, now this is not a correct assumption. A lot of times there is going to be a correlation between, your x variables, but assuming things are independent can make the model a little bit more useful and a little bit easier to deal with. Okay, so because the issue with the multivariate normal distribution is that you often need a lot of data to get the covariance between x variables, right? What's the covariance between x1 and x2? Okay, and what's the covariance between x1 and x3, and what's the covariance between x2 and x3, and so on and so forth. And if you have a whole bunch of these different x variables, then calculating covariance for every single one of them might require lots of data, right? So on the other hand, it's just a lot easier to just say, hey, there's no covariance. The covariances are all 0, okay? Probably wrong. But if we just assume the covariances are 0, we don't have to estimate any covariances. And then we can just keep going. All right, now, again, this is why it's called naive, because this is not a good assumption. It's a naive assumption to assume everything is independent. But again, we don't have to now we don't have to worry about estimating these things, because if you have a whole bunch of parameters to estimate and only a little bit of data, then what happens? Your parameter estimates now have a high variance, right? That's kind of an issue, right? Your estimate of the parameter is based only on a few observations. So your estimate of the parameter is now subject to just whatever random forces happen to appear in your data set. That could lead to problems. So here we're just going to assume everybody's 0. So here was our simulated data. These are the true kind of, this is the true contours that generated this data. And this time we are going to estimate the mean and the variances for class A and class B, but for the x1 and x2 variables separately. So rather than kind of doing the column means, I'm just going to say, hey, what's the mean of column 1 for the A observations? What's the mean of column 1 for the B observation? What's the mean of column 1 for the C observations? What's the mean of column 2 for the A observations? Mean of column 2, so on and so forth. For the variance, I do the same thing. What's the variance of column 1 for A? What's the variance of column 1 for B? What's the variance of column 1 for C? What's the variance of column 2 for A? What's the variance of column 2 for B? And so on and so forth. And I do this. So I'm just doing each variable one at a time for each of the different classes. So this is a whole bunch of values that I've got to estimate, right? And so if I estimate the contour lines under the naive assumption, what happens here? Now there's no covariance, okay? No covariance between x1 and x2. The difference is most profound for the green distribution. So in the green distribution, we know in the true data, there's high covariance between x1 and x2, okay? Everything kind of comes along in this diagonal ellipse here. And when I assume there's no covariance between them, this is what we get. We just say, okay, well, you got covariance, you got a variance of 3 in this direction, you got a variance of 3 in this, about 3 in this direction, and this is kind of what your ellipse looks like, all right? And it's just, the major and minor axes of your ellipse are parallel to x1 and x2, rather than being this diagonal ellipse, right? Whereas, you look at the blue and the red, it's pretty similar, right? It's pretty similar because in the true data, there was no covariance between x1 and x2 for red, no covariance between x1 and x2 for blue. And so if I kind of if I compare these ellipses in purple with the ones using the multivariate normal, the multivariate normal was able to estimate the covariance for green, okay? Whereas the naive ones, it's assuming there's no covariance between x1 and x2 for green, okay? For the multivariate, it estimated there was a little bit of covariance between x1 and x2 for red and blue, even though in the true distribution there wasn't. So, you know, but the covariance that it estimates is, you know, close to 0. So it's just ever so slightly off kilter. Whereas, you know, the green distribution, it really picks up that covariance, and in purple, it doesn't. So does this affect the quality of our predictions? Sure, it affects it a little bit, but the answer is it only affects it a little bit, which we're okay, and we can live with that. So this is what I have. I wrote the difference is most pronounced for the green dots, which were generated from a distribution with high covariance. But here with the naive assumption, there's no covariance. And so so the shape is quite different. All right, so let's just try this out again. How does it perform as far as classifying your dots? Let's try a dot at 0, 0. Okay. What is this going to be? Class blue, red, or green? We'll go through our calculations, and we use the same formula: likelihood times the prior divided by the marginal. But this time, the likelihood, I'm not going to use the multivariate normal anymore. I'm going to use the univariate normal distribution for one variable at a time, but I'm going to multiply it for all of my x variables. So I've got 2 x variables. I'm going to calculate the normal PDF for x1, and I'm going to multiply it by the normal PDF for x2. So instead of doing multivariate normal, I'm going to just say, okay, let's take our new observation. Let's look at the first value, and we're going to just use D norm. D norm is your regular old normal density. We're going to do D norm times the mean of x bar, not the mean, using the mean of what's the x bar of class A and what's the standard deviation of class A, okay? And then I'm going to multiply it by D norm, the normal density for the second x variable, using the mean of x2 for class A and the standard deviation of x2 for class A. Okay, so this is just a product of two normal PDFs. I want to give you a note or a hint or something. So for the next homework, right? So homework 4 is coming up, or I've just posted it. I'm going to have you do some, Bayes classifier, naive Bayes classifier. One mistake that a lot of students make, and they don't use the normal density, but they use instead of the PDF, they use the CDF. And in R, if you do P norm is the cumulative distribution function. That's the CDF, and it's going to give you different results. So make sure you use the density, D norm, rather than P norm, okay? So for the likelihood, always use the density. All right, so anyway, we do this for class A, and I do this for class B, all right? And the only thing that I'm changing is, okay, well, I'm using the mean of class B. What's the probability I get 0, 0 if we use the mean of class B, which is going to be close to 0, 0, I think, what, 0.2 and, something else. And then what about for class C, right? And again, we're not using the multivariate normal density. We're not using D multivariate normal. We're using D norm, and we're taking the product across two normal distributions, and we get this. This is my likelihood. My priors again are 1/3. The marginal is likelihood times the prior for all 3 possible classes. And then I do likelihood times prior divided by marginal, and I add them up for all of it. And so now class B is still the highest, 94% probability. Class C has a probability of around 5%. okay, which is quite a bit different from when we used the multivariate Gaussian, multivariate normal, okay? But still, we would say class B wins, okay? Class B is the highest versus, I think way back here, we got the answer to be like 99%, okay? And now it's 94%, okay? So something similar, but a little bit different. That's the naive Bayes classifier then. All right, let me do one more example, one more application, the naive Bayes classifier, and then we'll call it a day, right? So this is what, so students often ask, well, why this seems vastly inferior. The naive Bayes classifier seems vastly inferior to just the regular Bayes classifier. Why would I want to assume no covariance between x1 and x2, okay? Well, yeah, for the multivariate normal, sure. Assuming no covariance, maybe not the greatest idea, because the multivariate normal distribution, it's not that hard to deal with, okay? In your homework, I make you do the naive Bayes classifier, and I think that's fine. But it might feel like this seems inferior to the regular Bayes classifier where you use the multivariate normal. Okay, I can appreciate that argument. But here's a situation where I would say the naive Bayes classifier is going to do a much better job, okay? And we can use the naive Bayes classifier as a document classifier. And the reason why the naive Bayes classifier is going to be preferable in this case is the way we're going to treat our data is we're going to treat it as a, quote, bag of words, okay? And so we're going to look at all of the words that we have in say a document. A document can be anything as short as a sentence or, an actual document or article or paragraph or tweet or whatever it is. And we want to try to classify maybe what category this document belongs to, okay? The reason why the naive Bayes classifier is preferred for this is that we don't have to calculate the covariance between words, okay? Now, is there covariance between words? Yes, there is, okay? Meaning, because our variables will be how many times did this particular word appear, right? So it could be like, how many times did the word A appear? How many times did the word aardvark appear? How many times did the word, I don't know, what other A words are there? AA and armadillo and, okay, and, and what's the covariance, right? And so certain words are going to appear highly together, right? So things like good day, good and day will probably have a higher probability of showing up together than maybe other combinations of words, right? Like, maybe plate and fork have a high probability of showing up together versus, plate and, I don't know, plate and bedroom, okay? Lower probability of showing up together, right? Lower covariance. But the question is, you think of every single word in the language, okay? I don't know how many words there are. Let's say there's, 50,000 words that we're going to consider, all right? And there's more words than that, but let's say we're going to consider 50,000 words. And now you have to calculate the covariance between every single possible combination of words. And that's just too many. That's too many. We don't want to deal with that. So, so we're not going to deal with that. Okay. We're going to just say, we're just going to assume no covariance between words. Every word has the equal chance of showing up with any other word, which is not correct, but it's easier to kind of think of it that way than to try to figure out, which combinations, which two words are more likely or less likely to show up together. And gosh, having to deal with that. Okay. Now, a bag of words, again, is a model, is not a great model. Okay. The bag of words says, any document can be treated as you just take the words, and it's as if you lose the structure of the document. You're just looking at the words themselves and how many there are, right? The order of the words don't matter, right? If you throw objects into a bag, there's no order, right? In a stack there's an order. You can have the first, the second, the third, and the fourth element. If I give you a bag of stuff and I say, give me the sixth object in the bag, you have no idea what object I'm talking about, because there's no order inside of a bag, right? There's no, give me the sixth object in a bag. That doesn't make sense, right? Reach into your backpack and pull out the fifth element. That doesn't make sense, right? In a stack, sure, you can say, okay, pull out the fifth element in a stack. And so in a bag of words, the order doesn't matter. There's no order. You just kind of take these things. Now, document, again, is a loose term. It could be a literal document, but it could be something as simple as a sentence. So, shortcomings of the bag of words is that the order doesn't matter. We're just looking at how many words appear and the count of the words, okay? So if this is your document, it is bad, it is not good. The bag of words will say, okay, it appears twice, is appears twice, bad appears once, not appears once, and good appears once, okay? Versus compare this document, it is bad, it is not good. Compare that to it is good, it is not bad, okay? The bag of words is going to have the same word counts. It, two, is two, bad one, not one, good one. Both of these documents have the exact same word counts according to the bag of words model, and both of these documents will get the exact same classification, okay? Despite having different meanings, these, according to the bag of words model, these two documents are identical. Now we know in English that's not how it works. The order of words do matter. So this is just a major shortcoming of the bag of words model, okay? And so this is, so one thing, I don't want to poo-poo anybody's projects here, but a lot of times I see like sentiment analysis projects where we go on Twitter and we scrape some Twitter data and then we want to do some sentiment analysis. And then if you're using a bag of words model, it's like, it's gonna suck a little bit, because both of these documents are going to get the same classification with a bag of words model. And so, for certain sentiment analysis things, I don't know if it's really going to be that effective, because these obviously say very different things. Bag of words model is going to say, oh, they're the same. Okay. So that's a major issue of the bag of words. And so just be aware of that, and don't try to use the bag of words model in places where, oh, you know what? The orders matter, right? You can kind of expand this by dealing with like 2 grams or n grams rather than dealing with one word at a time, but now your model's like way more complicated. Okay, so a document classifier requires what we call a lexicon, and the lexicon has word probabilities, right? So here I have an example lexicon. This is a very, very, very simple lexicon where there's only basically 8 words in our entire vocabulary. Our 8 words are king, queen, princess, knight, rook, good, evil, and bored, okay? And this lexicon, we have it defined for 2 classifications. The document could be about fairy tales, or the document could be about chess. And again, silly example, but basically, if you wanted to do a document classifier, you would have to create your lexicon. And so you'd say, okay, you know what, we're going to try to classify whether or not this document is about politics. And you would have a lexicon of probabilities for words that belong to politics. So politics maybe would have words like senator will have high probability, and representative and house and senate and I don't know what else, party and things. Those words will have higher probabilities, versus like other words will have lower probabilities, right? Or you might say, okay, let's see if this document is about sports, okay? And with sports, certain words will have higher probabilities. You'll have like player and coach and team and field and ball, and those words will have a higher probability, right? And so you would need to have kind of a lexicon for whatever categories that you're dealing with, and you would have to adjust the probabilities here. Okay. And so I said, okay, if we're talking about chess or fairy tales, the word queen might have a high probability in both of those scenarios. Okay. Whereas the word princess, that's going to have a higher probability for fairy tales and a very low probability for chess. Okay. So here I'm just doing 1%. Okay. Probably it's even smaller than 1%, but could a chess, could you mention a princess if you're talking about chess? Sure, maybe you played chess over at the princess's house. I don't know, right? Knight is a word that shows up a lot in fairy tales and also a word that shows up a lot in chess, whereas the word rook, okay, shows up more in chess and not very often in fairy tales. Okay, maybe talking good could show up in either, right? You could have the good fairy or the good princess or whatever, and you might have the word good in chess if you're talking about a good move, right? A good play. Okay, whereas the word evil, we often have like the evil queen or something like that in fairy tales, but the idea of something being evil in chess, probably that's it would be a little bit extreme to talk about. So anyway, these are kind of the different lexicons that I have. All right, let's try an example. Okay. Oh, so how do we get the lexicon? So you might train or develop your lexicon by kind of scanning in a whole bunch of documents where and you give it labels, right? So you say, okay, I know this document's about politics. I know this document is about sports, and you scan it and you have it parse it out, and you have it count up the count of each of these words and their probabilities and something like that. Okay, and it's common practice to remove stop words, things like this, is, to, a, just words that don't really add meaning or context because they just show up all the time. So as far as classifications, we probably just throw these words away. Okay, so let's say we have this sentence: the evil queen sent the evil knight to capture the princess. All right, so I'm being a little redundant, but just let's say this is the sentence. Now, do you think this sentence is about chess or is it about fairy tales? Okay, so the fact that we've got the evil queen and the evil knight and the princess, this feels like, okay, it would be quite extreme. Can't imagine this sentence coming up in chess. So anyway, we do the bag of words and we say, okay, well, what are the count of words that show up in our sentence, right? We got queen shows up once, princess shows up once, knight shows up once, evil shows up twice, right? Basically, all of the other words that aren't part of my lexicon, they just don't count. Okay, so again, very simple lexicon. This is what we've got. So now I'm going to say, okay, well, what's the probability? Let's just do the likelihoods. Okay, so the Bayes classifier or naive Bayes classifier, you'd have the likelihood. You'd also have the prior and the marginal. But the marginal is found by taking the likelihood times the prior across all classes, and the prior, let's just say the same as 50-50. All right. So here, let's just worry about the likelihoods. Okay. The likelihood, I'll just say, okay, what's the probability of getting queen if it's about a fairy tale? Queen fairy tale is 20%. What about princess if it's a fairy tale? So going back, princess fairy tale is 25%. Knight for fairy tale is 20%. And the word evil for a fairy tale is 11%. Okay. So we take this product, 0.2 times 0.25 times 0.2, and then evil showed up twice. So we're going to raise it to the second power, 0.11, 11% squared. We get 0.000121. Okay, so this is our likelihood here. Let's compare this with the likelihood if it was a chess, if it was about chess. What's the likelihood of getting this data if the story was about chess? Okay, so queen for chess is 20%. Princess for chess, I'm sorry, queen for chess is 20%. Princess for chess is, 1%. Knight is 15, and evil is 1%. So if we do this, okay, 0.2 for queen, 0.01 for princess, 0.15 for knight, and 0.01 squared for evil showing up twice. Okay, now the likelihood is way, way, way smaller, 0.000000003. Okay, so much, much smaller. Okay, for chess. So between these two, we'd say, okay, definitely about fairy tales. Okay. All right, what about this? The queen captures the knight. The queen captures the knight. So this one, well, I don't know. Okay. If we did it for fairy tales, queen has probability of 20%. Knight, I think, was 20%. For fairy tales, we have 0.04. For chess, it was 0.2 times 0.15. We get 0.03. So basically, these values are very comparable for this sentence. Queen captures the knight. Okay. Okay. What about queen captures the rook? Okay. Queen captures the rook. Whoops. Oh, I messed up. This is a typo. So queen captures the rook. Okay. Queen and rook here. So for fairy tales, rook has only 0.01, whereas for chess, 0.2. So we take these two things, the answer is going to be 0.002 versus 0.04. So quite a different different probabilities if we're dealing with queen captures rook. So the queen captures the rook now is much more likely to be about chess. Queen captures the knight is a little bit more ambiguous. It could be about either. The evil queen sent the evil knight to capture the princess is much more likely to be for a document of fairy tales. Okay. And you can imagine just expanding this, right? Where you just need a bigger lexicon, more different categories for possible documents. And now you have a simple document classifier by just kind of going through and counting how many times a certain word appeared. All right, that's all I've got for you today. Let me give you your last view quiz answer. Last view quiz answer today is the letter A. A as in apple. A as in apple is your last view quiz answer. All right, thanks everybody. We'll go ahead and end here.